Okay, so we've reached the final module, and this is where it gets really exciting. We're going to look at some of the problems that astrophysicists are grappling with at the moment. First of all, we'll look at the so-called dark ages of the universe. This is a time in the universe's history that we know almost nothing about. We'll be looking at black holes, how they work, do they exist, and what they can teach us. And we'll be talking to real researchers who are working on these problems at the moment. And finally, we'll be addressing one of the most fascinating questions of all. Are we alone in the universe? We'll be looking at how we might use radio telescopes to detect other civilizations. So let's recap quickly how the universe looks on different scales and how far away all of those things are. We'll start with the moon. The moon is around about 1.5 light seconds away. So when you look up at the moon in the sky, you're already looking backwards in time. It's taken the light from the moon 1.5 seconds to reach your eye, and so you're seeing the moon as it was 1.5 seconds ago. If we think about the solar system and the other planets that go around the sun itself is 8 light minutes away. So you see the sun as it was about 8 minutes ago, and the various planets are different distances away, but we're talking about light hours. It may have taken several hours for light to reach us from the distant planets. Then we have a huge step up in scale, going from the local solar system to other stars. Even the nearest star is almost 4 light years away. And some of the stars that we see in the night sky may be thousands of light years away. So now, as we look at the stars, we're really beginning to look backwards in time. If we then go out to the scale of other galaxies, then we're looking much greater distances. It's just about possible to see a few of the nearby galaxies with the naked eye. And so when you're looking at those galaxies, you are looking backwards in time millions of years. And finally, with our most powerful telescopes, we are actually able to see so far away that we're looking back most of the way to the time of the Big Bang. And we can see the earliest galaxies which formed in the universe. So the fact that the speed of light is finite, light and other electromagnetic radiation can't travel infinitely fast. This gives us a really useful window on the universe. Every time we look at something, we're looking backwards in time. Even if you look at something just a few centimeters away from your face, it's taken time, tiny amount of time for that light to travel to your eye. If you look at something very far away in the universe, then you're looking very, very far back in time. So all the time we have this thing called a world line. If we have distance along here and time up here, we see a slice through the universe. So if we have something that's a very small distance away, then we see it a small amount of time in the past. If we have something that's a very big distance away, then we will see it as it was a long time in the past. For something that's a particular distance away, for example, if we see a galaxy, if we look at that galaxy, we will see it evolving, but it will remain in the past. So what all of this means is that we have a direct line of sight right the way back to the Big Bang by looking at different distances away. So what do we see? Well, here's a quick summary. The earliest thing that we can see in the universe was straight after the universe went from opaque to transparent, the cosmic microwave background that we've discussed a couple of times already. Then we can look right the way back in time and see new galaxies very soon after they've formed. And then we see how those galaxies have evolved and moved away from each other into the universe that we see today. If we go back to that time, though, between the cosmic microwave background and when the first stars formed and the first galaxies formed, there's a bit of a gap. We call this gap the dark ages, and we call the time when the first stars were beginning to form the epoch of reionization. And this is a really interesting time in the universe's history. Unfortunately, this time in the universe's history is very, very difficult to study because the universe consists almost entirely of neutral hydrogen. Now, neutral hydrogen isn't like the plasma that we see in the early universe, which is very bright and giving out lots of radiation. And it's not like the stars that we see once they have formed, where they're very bright and they're giving out radiation we detect. So how can we actually manage to detect neutral hydrogen